Mass of this object is 50 kg. These both bodies accelerate with the same speed towards Earth. If I ask you to catch one object out of these two objects, which object would you choose to catch? I am sure you will choose the object of mass 5 kg. Is it because the mass of 5 kg is less than 50 kg? The answer in physics is no. It is because the momentum of 5 kg body is less than the momentum of 50 kg object. In physics, we define momentum as the cross product of mass and velocity. We denote momentum by P. Hence, P is equal to mass and to velocity. We know that velocity is a vector quantity. Hence, momentum is also a vector quantity. The direction of momentum is same as the direction of the velocity. Now, how can we calculate the SI unit of momentum? As we know that momentum is equal to mass into velocity. Our momentum is equal to m and to v. The SI unit of mass is kg and the SI unit of velocity is meter per second. Hence, the SI unit of momentum is kg meter per second. This unit of momentum tells us just the quantity of a motion present in a body or in a mass. Now, how can we calculate the momentum of an object? Let me give you two cases. In case 1, if a person is standing on a road, suddenly a bicycle of mass 50 kg moving with a velocity of 60 meter per second hits the person. As a common observation, the person would only be injured. Now consider the same person in case 2. If this person is standing on a road, now suddenly a truck of 2500 kg moving with the same velocity of 60 meters per second hits the person. As a common observation, the person may die. Can you guess that a person in case 1 is only or merely injured, while the person in case 2 is either died or in serious condition? Although both the bicycle and truck were moving with the same velocity of 60 meters per second. I hope that your answer would be the difference in masses. If it is so, then you are 100% right. Let me explain these two cases in physics. In case 1, the mass of bicycle is 50 kg. It means mass is equal to 50 kg and its velocity v is equal to 60 meter per second. Hence, the momentum p of the bicycle is equal to mass of the bicycle and the velocity of the bicycle. Now, putting values in the formula, p is equal to 50 kg and to 60 meter per second. We get 3000 kg meter per second. Hence, the momentum of bicycle is 3000 kg meter per second. In case 2, the mass of truck m is equal to 2500 kg, while the velocity of the truck is 60 meters per second. Hence, the momentum of truck p is equal to mass of the truck and to velocity of the truck. Thus, p is equal to 2500 kg and to 60 meters per second. We get p is equal to 150,000 kg meter per second. So the momentum of truck is 150,000 kg meter per second. This shows that the momentum of a bicycle is smaller than that of the momentum of a truck. Therefore, a person is merely injured in case 1 when it was hit by the bicycle, while in case 2, the person got serious injuries are dead when it was hit by the truck. At last, let me teach you, does a stationary body possesses momentum? To answer this question, let me give you another example. If a car of mass m is stationary or at rest, its velocity v is equal to 0 meter per second. Hence, its momentum is equal to P is equal to m into v. Thus, P is equal to m into 0, or P is equal to 0 kg meter per second. It shows that if an object is at rest, its momentum P would be 0. Or we can say that the momentum P of an object would be 0 if the body is at rest. I hope you have learned the fundamental concept of momentum. Thank you very much for watching this video.
Okay. Yes, that is just an intro to a topic called momentum. And Martina, for you, you don't have any challenge in this. In other words, what you've been looking at basically in this video is one. We just wanted to find out basically what is momentum. And we have defined momentum as the product of mass and velocity. In case you add on the word linear, then it means that it is the product of mass and velocity for a body moving in a straight line. But the most important thing here is just to know that it is about momentum, it is about multiplying mass and velocity. I've also said that the SI unit is a kilogram times the SI unit of velocity, which is a meter per second. Another thing that you have noted is that momentum is a vector quantity. It is a vector quantity, meaning that it has both the size and the direction. That's how we define a vector quantity. And we have said that there are two factors that affect the size of momentum. Factors affecting size of momentum. Martina's internet, I think, is disturbing. Factors affecting momentum. There are two of them. Can you remind me of those factors?
Mass and velocity.
Mass and velocity, very good. Meaning that in case the mass increases, from momentum is equal to mass times velocity. If the mass increases, momentum also increases. That's why a truck which is very heavy, if it is moving at the same speed with a bicycle which is lighter at the same speed, they are both moving at the same speed, but since the difference in masses is here, then the car possesses a bigger momentum, a bigger quantum of energy. Likewise, in case you have a truck which is moving slowly, and then you have a small bullet which is moving very fast. So at one point, those two bodies can be moving with the same momentum, because if momentum is equal to mass times velocity, it means that the big car, even if it is moving with a small velocity, may acquire the same momentum when we have a bullet which is having a small mass but moving with a very high velocity. In other words, in short, the bigger the mass, the bigger the momentum. And the higher the velocity, the bigger the momentum. That's what we've looked at in this short video here. Now, another thing that we need to note, of course, you may not write all of these because you looked at them in your O level, but you need to know that we shall simply base on that idea of O level and build on that at this level of ours. Then, last time when you're not with us, as I'm waiting for this girl to come back, we talked about what we call Newton's laws of motion. Newton's laws of motion. And can you remind me of those laws? We have the first one, we have the second one, and then the third one. Any that you remember? Yes, is there any that you remember? Sorry, let me just take it back. Yes, is there any that you remember? The first, the second, and then the third. Martina, you're on and off. We're just having a quick review here. Newton's laws of motion. Newton's laws of motion.
Hello?
Yes, I'm hearing.
You keep on going on and off, so like I don't really hear you well.
I think it's stable now.
Okay.
It is not data. I was just
It can't be data. I know you have data. Maybe like connection
someone was calling
going
me.
on and off.
Someone was calling me.
Oh. Okay. The first one, let me see if I remember. A body remains in its state of rest or uniform motion in a straight line unless an external force acts on it.
That is very good. That is correct.
The second one, the rate of change of momentum is directly proportional to the magnitude of the applied force.
Okay, that is also almost correct. You always add on that and takes place in the direction of the force.
Wrong.
You always add on the direction. Yes,
okay.
that the rate of change of momentum of the body is directly proportional to the applied force and takes place in the direction of the force. You should always add that there. And then finally, for every action, there's an equal and opposite reaction. Okay, then
Yes.
remind me about the principle of conservation of momentum. Yes. Principle of conservation of momentum.
Could Martina help on that?
Okay, it's fine, it's fine. But do you remember the equation? Anyway, the equation is like this. The equation is like this, that M1 U1 plus M2 U2 is equal to M1 V1 plus M2 V2. In other words, total momentum
before collision is equal to momentum after collision.
Very good. Is equal to total momentum after collision.
Yeah.
After collision. But you don't state it like that. This is just a numerical expression. The conservation of momentum, the principle of conservation of momentum states that when two bodies collide, total momentum before collision is equal to total momentum after collision, provided no external forces act on the system. That is what we have as the principle. Or it states that for a system of colliding bodies, total momentum is always conserved, provided no external forces act on the system. So that is where I want us to begin from. And Martina, we discussed this in the previous lesson. And I just want to begin from here, and then we do some more examples, and then we continue. But before we do that, we can have a quick recap of the types of collisions here. So, Andre, you can start from here. Can I start writing from here? Collisions. This one simply means interactions. Simply means interactions, or simply coming into contact. And the types are basically three. We have what you call the elastic
and inelastic,
or perfectly elastic. Then we have the inelastic, and then we have the perfectly inelastic.
okay.
Yeah, like this. So I'm going to use a table to distinguish the three of them. First of all, what do you remember? What is an elastic collision?
I remember that in elastic collision, the momentum is conserved, right?
Okay, correct.
Then in elastic, the momentum isn't conserved.
Okay. Martina, what did you say about this in momentum? Yes, Martina? Your microphone is on. I mean, is off. Martina?
Well, I think her data,
Yes,
as in.
Okay, yes, I was saying
Okay,
that what do you
she's
remember
back.
about momentum as far as types of collisions are concerned? Is momentum conserved or not conserved?
Momentum is not conserved.
Is not conserved. All right. So, just a correction here. In all of them, whenever we talk about collision, is momentum is.
But teacher, do you know we didn't learn collisions?
In the previous lesson?
We have notes on it. We have notes in it, like that's where the notes stop from
Okay,
doing.
we can discuss this. We can discuss, but Martina.
Yeah, yes, they are the notes, but we didn't talk about.
Yes, I was
it.
saying that in the previous lesson that we had on Monday, Martina, with you at 9 p.m., we discussed this. But anyway, it is okay in case you've forgotten, we can remind ourselves. So we said that in all of them, momentum is conserved. And actually, I said that you can write this, and even in perfectly elastic, momentum is conserved. In other words, what does it mean? It means that when two bodies collide, the total momentum before collision is always equal to the total momentum after collision, provided the external forces act on the system. So in all of the three of them, momentum is conserved. And how about kinetic energy?
Oh, okay.
How about kinetic energy? In elastic collisions, kinetic energy is conserved. In inelastic, it is not conserved. Let's write this in a table. It is just a summary. And then in perfectly inelastic, it is also not conserved. I'm going to explain this again in an example. And then.
Okay, but like before, teacher, what's the difference between inelastic and perfectly inelastic?
And this is the difference. This is the difference. As far as separation is concerned, separation after collision, we can say that bodies separate after collision. Here, bodies separate, and then here, bodies do not separate. Bodies do not separate.
Hello?
Yes, can you hear me? Hello, ngenda kukubira lindako. Okay. Someone was disturbing me here. I'm sorry for that. Sorry for that.
Oh.
I was saying that we have elastic, inelastic, and then perfectly inelastic. And perfectly elastic is the same as simply elastic. Perfectly elastic. But perfectly inelastic is different from inelastic. That's why I'm separating them like this. So in terms of momentum, I've said that this one momentum is conserved. This one is conserved. And this one is also conserved. I'm just writing a summary here. I'll send you the notes maybe later on. But still you need to...
Oh, I think we have it in our notes.
It is fine.
Okay.
Fine. So kinetic energy, you're saying that this one is conserved. This one is conserved, not conserved, sorry. Not conserved. And this one is also not conserved. Not conserved. Then for separation after collision, this is another difference after collision. And I'm saying that for perfectly elastic or simply elastic collision, bodies separate after collision. Here, they do not, they also separate. They also separate after collision, separate, and then here, they move together after collision. In other words, do not separate.
Okay.
Not separate. And then, yes, those are the major differences. Examples that you can give here is, for example, a collision. For example, collision of gas molecules. Collision of gas molecules, of ideal gas molecules. Now, we're talking about kinetic energy not being conserved. It means that when the bodies collide with each other, that energy is transformed into other forms. In other words, it can be changed to forms like, for example, sound energy, heat energy, and others. But if it is perfectly elastic, that energy is not lost in any other form. It remains as kinetic energy. So one body gives all its energy to another in form of kinetic energy. And that's why the total kinetic energy before collision is always equal to total kinetic energy after collision. That is for perfectly elastic. But for inelastic and perfectly inelastic, that energy is transmitted to other forms. So examples of perfectly inelastic, for example, here you can talk about maybe a bullet being embedded in a wooden block like that. Someone fires a bullet and it enters a wooden block, and then the two move together after collision. That is an example of perfectly inelastic collision. Okay, for inelastic, it is not so common, and I may not give an example on this as per now. So, but basically, we shall be looking at elastic and then perfectly inelastic collisions. That is what we will be looking at shortly. Now, after having looked at all of these, I hope that I can rub off.
Yeah.
Yeah. So, I need to remember, in summary, in summary, I need you to state the principle of conservation of momentum. That one. And then 2, I need you to differentiate between the types of collision. Those are my questions there. Now, a question can come here, which we're going to do here. A question says that use Newton's laws to verify or to prove, let me use prove. You can write this question as well. To prove the principle of conservation of momentum. Principle of conservation of momentum. And you can simply write this. We're going to work out together. Hope that you're writing too, because we need to move together. So,
Yeah.
yes, so we can say this, that we consider two bodies. Remember that in momentum, we're going to simply prove that total momentum before collision is equal to total momentum after collision. Collision. So we shall say that consider two bodies of masses M1 and M2 moving with velocities U1 and U2. If they collide with each other for time t, okay, so in 10 minutes we'll be shutting down, and you log in again. In time t, and the velocities change to v1 and v2 respectively, then, yes, when you reach there, let me know.
Where's Martina gone? Her internet is very shaky.
I don't know. I'll just get her the video.
Okay.
Just get her the video. Let me get her. Yeah.
Okay, I'm done.
Okay. So, we just need to note for conservation of momentum, we use the equation is M1U1 plus M2U2 equals to M1V1 plus M2V2. And for conservation of kinetic energy, we use a half M1U1 squared plus a half M2U2 squared is equal to a half M1V1 squared plus a half M2V2 squared. Otherwise, in case you have a numerical question and you compute and then the kinetic energies are different, then it means that the collision was not elastic. The collision was not elastic. Now, one other thing before you go to the questions, one other thing is this. Note, you can also write it down that for a perfectly elastic collision, for a perfectly elastic collision, the relative change, okay, let me just write it like this. The relative initial velocity is equal to the relative final velocity. In other words, what I mean here is this, that U1 minus U2 is equal to V2 minus V1. Now the question is prove. We're now back to the math. Prove. So you're going to meet questions whereby you're going to be solving some questions and they'll need you to use this equation here. What you can do, one thing that you need to remember is that since you know that the equation for momentum is this, and the equation for conservation of kinetic energy is this, then these two equations here give you this expression here. In other words, if you don't remember this, then you go back to first principles and